Alright, Chapter 3, Waveforms, Wave Generators. Non-resident training course, September 1998, Navy Electricity Electronic Training Series. Module 9, Introduction to Wave Generation and Wave Shaping. Alright, Chapter 3, Waveforms, Wave Generators. Upon completion of this chapter, you will be able to explain the operation stable, non-stable, bistable, multi-vibrators, explaining operation block oscillator, explain operation sawtooth generator, explain operating the trapezoidal wave generator, explain how to jump voltage and produce trapezoidal wave generator. Waveforms. This chapter will present the method of generating waveforms. Before you begin to study how the waveforms are generated, you need to know the basic characteristics of the waveform. This section will discuss basic periodic waveforms. Periodic waveforms. A waveform which undergoes the pattern change but returns to its original portion and repeats the same pattern is called the periodic waveform. Periodic waveforms are non-syncytial, syncytial, except for the sim wave. The periodic waveforms which have been discussed in sim waves, square waves, rectangular wave, sawtooth, and trapezoidal wave and trigger pulses. Sim wave. Each completed pattern of the periodic waveform is called a cycle, as shown in the sim wave in a Figure 3.1 View A. The sim waves are presented with the Neets Module 2, alternating current transformers, Chapter 1. Sim wave, square wave, rectangular wave, sawtooth wave, trapezoidal wave, trigger wave. Alright, your square wave. The square wave is shown in Figure 3.1 with a view B, but this is shown with the two alterations for the equal duration. Second presentation of each of the complete cycle. Figure 3.2 shown with the breakdown of the square of the wave, and then figure that you should view. Throughout the square wave discussion, the amplitude is measured vertically, with the time of the complete cycle is measured between the corresponding points of the wave time 0 2 to time 2 to 2 0 to 2 2 and 2 1 to 2 2 8. Time cycle pulse wave amplitude positive alteration leading edge trailing edge negative alteration rinse time rise time fall time. One alteration is called the pulse for the time of the one complete cycle. It's called the pulse repetition time, or PRT. The number of times of the 1 second cycle of the representative itself is called the pulse repetition frequency, or pulse repetition rate. If each of the alteration of the Figure 3.2, the microfarads, 200 microseconds over the pulse repetition time will be 400 microseconds. The pulse repetition frequency frequency will be 2500 hertz. In the following example, provide illustrated mathematical relationship between pulse repetition frequency and pulse repetition time. Pulse repetition frequency is equal to 1 over the pulse repetition time. Pulse frequency is 400 microseconds. Your pulse repetition frequency is equal to 1 over the pulse repetition time. 1 over 400 microseconds is 250 hertz. You should readily see that pulse repetition time is just inverse for the pulse repetition frequency. Therefore, given that the pulse repetition time is equal to 1 over the pulse repetition frequency, or 1 over pulse repetition is 2500 hertz. So 1 over 125 hertz is 400 microseconds. The length of the pulse is measured in time. The time interval 0 and 1 is referred to as pulse width. The left side of the pulse is called the leading edge. The right side is called the trailing edge. The time is required with the voltage carried with the chain with the amplitude interval with the time need with the voltage go from 0 to 100%, or from 100% to 0%. With the maximum value is called transit interval. The two types of the transit intervals are rise time, fall time. The rise time is more accurately defined as the time required for the voltage to build up to 10% to the 90% of the maximum amplitude point. The fall time is the time required for the voltage drop from 90% to 10% of the maximum amplitude time. In the next text, you will be presented with information for the waveforms appear have the instantaneous rise and fall time. These are done with simultaneously presentation of the material. In reality, these waveforms do have rise and fall times transit intervals. Alright, rectangular wave. Similar with a square wave, the difference for the rectangular waveform is the two alterations of the waveform's unequal duration. Figure 3.1 View C show that the negative alteration pulse is shorter in time than positive alteration. The negative alteration could be represented in as long as there are two alterations either way with the appearance of the rectangle. Your sawtooth waveform is shown in Figure 3.1 View D. A sawtooth wave that resembles the teeth of the saw blade that was rapidly vertical ride with the voltage of the transfer time 0 and time 1 with linear straight time 1. If the voltage abruptly falls, there is essentially no time and keep the previous static value. The voltage remains at the voltage with time 2. When it again linear rides, you can see the action of the oscilloscope where there are two voltages input location vertical and horizontal. If you apply the linear voltage of the vertical input with the electron beam, will be forced to move in the vertical direction of the CRT. Our linear voltage applied to the horizontal input with electron beam to move across the cathode ray tube. The application of the two linear voltage vertical input, one horizontal input at the same time will cause beam to move both the vertical and horizontal direction at the same time. Then is how the sawtooth wave is made appear with the oscilloscope. But you refer to Figure Neets Module 6 electronic emission tubes power supply chapter 2 of your review oscilloscopes. Your trapezoidal wave. The trapezoidal wave looks like a sawtooth wave on top of the square of the vertical wave, as is shown Figure 3.1 View E, with the leading edge of the trapezoidal wave is called the jump voltage. The portion of the wave is linear with the rise with the slope. The trailing edge is called the fall and the decay. A trapezoid wave is achieved with the first deflection current over the electromagnetic cathode ray tube and is found with the television radar display electronic magnetic cathode ray tubes use the coil of the deflection system linear rise of the current required for an accurate horizontal display of the square or rectangular wave portion provides jump voltage for the linear rise of the current through the resistance of the coil that will be explained further in discussing the trapezoidal sweep of the generator. Your trigger is very narrow pulse as shown in Figure 3.1 View. After the trigger pulse are normally either turn off, other circuits on or off. Wave generator. Non-sagittal oscillator generate complex waveforms such that as discovered the cover the output of the oscillator generally characterized by the sudden change relaxation for the oscillators are called the relaxation oscillators. The pulse repetition rate of the oscillator is usually governed with the trend of the discharge timing of the capacitor and shape of the resistor. However, some of the oscillators contain the indicators that, along with the circuit resistance, affect the output frequency. There is the resistor capacitor, inductor capacitor networks, which oscillator circuits are used with the frequency determination. The category of the relaxation oscillators are multiple vibrators, block oscillators, sawtooth, and trapezoidal wave generators. Many electronic circuits are not in on condition of all time. The computers, for example, the waveforms must be turned on and off specific changes, length of time. The time intervals of the vary over the microsecond and several thousand microsecond square rectangular waveforms normally used to turn on such circuits and on and off to cover the sharp leading trailing edge of the wave, make them ideal for timing purposes. Multivibrators, the type of the circuit that must often use with the generator square with a rectangular wave of the multivibrator. The multivibrator shown in Figure 3.3, basically two amplifier circuits arranged with a regenerative feedback. One amplifier is conducting while the other is cut off. 3.3 shows a stable multivibrator, shows the transistor 1, transistor 2, grounded, resistor 1, resistor 2 capacitor, resistor 3, resistor 4 capacitor. Show that they're using two amplifiers with a transistor and output 1 and output 2. Voltage current collector. When the input signal of the amplifier large enough for the transistor can be driven with the cutoff of the collector voltage with the almost voltage current collector. However, the transistor driven in saturation of the collector voltage that will be about 0 volts. A circuit is designed to quickly from cutoffs of saturation will produce the square rectangular wave and its output with the principal use of the multivibrators. Multivibrators classified according to the number of the stable states. If the circuit is stable, exists when the circuit operation is essentially constant with the one transistor remain with the conduction when the others remain cut off until the external signal is applied. Three types of multivibrators are astable, monostable, and bistable. The astable has no stable state. No external simple applied with the transistor alternately switch cut off at the saturation frequency determined by the resistor capacitor time constant of the coupling circuits. Your monostate circuit has one astable state, one transistor conducting while the other is cut off. The signal moment is signal must be applied to change the condition period of time to determine the interval of the resistor RC component of the circuit will return to the original condition where it remains until the next signal arrives. Your bistable multivibrator has two stable states that remains on one side and one stable stage until the trigger is applied. It then flips the other stable condition remain with until the other trigger is applied. The multivibrator change with the back flops first stable state. Your Astable Multivibrator. The Astable Multivibrator is known as a free-running multivibrator. It called free-running because of the alternates between the two different output voltage levels during the time is on, but the output remains each volt for the definite period of time. If looked up at the output of an oscilloscope, you would see the continuous square rectangular wave. This is Astable Multivibrator, 2 outputs, no inputs. Look at the multivibrator, figure 3.3. Again, the Astable Multivibrator. The Astable Multivibrator says the oscillate, and understand the Astable Multivibrator oscillates. Assume that transistor 1 saturated, the transistor 2 cuts off on the circuit is in drive. The situation is shown in figure 3.4. The transistor 1 saturated, transistor 2 cut off because of the circuit is symmetrically. Therefore, resistor 1 is equal to resistor 4, resistor 2 is equal to resistor 3, capacitor 1 is equal to capacitor 2, transistor 1 is equal to transistor 2. It is possible the transistor will actually conduct whenever the circuit is energized. For this reason, either the transistor may be assumed to conduct for the circuit analysis purpose. Essentially, all the currents of the circuit flow, but the transistor 1 offers no resistance for the current flow. With no for the capacitor 1 is charging, the transistor 1 offers no resistance for the saturated state, but the rate of the change. But the capacitor 1 depends only on the time constant of the resistor 2 and capacitor 1. This we call is the TCRC. Note that the right hand of the capacitor 1 is connected with the base of the transistor 2. Which is now cut off. Let's analyze what happens. The right hand of the capacitor 1 becomes increasingly negative in the base of the transistor 2 becomes sufficiently negative. The transistor 2 will conduct after the period of time of the base for the transistor 2 will become sufficiently negative to the transistor 2 to change the state for the cutoff of the conduction of the time necessary for the transistor 2 to become saturated, determined of the time and the constant of resistor 2 capacitor 1. Note, the next state is shown in figure 3.5. The next voltage accumulated with the right side of the capacitor 1 is called capacitor 2 to conduct the now flowing sequence, even that takes place almost simultaneously. Transistor 2 starts conducting, quickly saturates the voltage output, but the 2 changes from the approximate voltage current collector to approximately 0 volts. The change in the voltage is coupled through the capacitor 2 base of the transistor 1, forcing the transistor 1 to cut off. Now that transistor 1 is cut off, the transistor 2 is in saturation. The circuit is shown in figure 3.6. Alright, 3.5 shows the stable multivibrator. 3.6 shows the stable multivibrator. Transistor 2 saturated. You know, for the figure 3.6 of the mirror image of the figure 3.4, and figure 3.6 of the left side of the capacitor 2 become the more negative the rate, depending on the type of the circuit, but the constant of the resistor 2 and resistor 3 and capacitor 2. Left side of the capacitor 2 becomes more negative the base for the transistor 1, also becomes more negative than the base for the transistor 1 becomes negative enough to allow transistor 1 to conduct. Transistor 1 will again go into the saturation, result with a change in the voltage output, but the 1 will cause the transistor 2 to return to cutoff state. Alright, look at the output waveform of the transistor 2 is shown in the figure 3.7. The output voltage from the either output multiple vibrator alternates approximately 0 voltage to approximately negative voltage current. Remains at each state with a definite period of time may remain range microsenses as much for the second or two. There was some application time period with a higher voltage current collector time period. Lower voltage, 0 voltage will equal with other applications require different higher lower voltage times. For example, times getting in time and gating circuits are often different poles, which is shown in figure 3.8. Figure 3.8.7 shows the square wave output of the transistor 2, time determined by the resistor 3 and capacitor 2, transistor 2 cutoff, time determined by the resistor 2 and capacitor 1. Alright, time determined by the resistor 3 and capacitor 3, transistor 2 cutoff, rectangular waves, or time determined by resistor 2 capacitor or transistor 2 saturated and cut off. Frequency stability. Some stable multivibrators have the high degree of the frequency stability. One way to obtain the high degree of frequency stability with apply with the trick of the figure 3.9 view. A show of the diagram trick with the stable multivibrator time interval T0, the negative input trigger the base of the transistor 1 through capacitor 1. Causes transistor 1 to go into saturation while the transistor 2 cut off. The circuit will remain in this condition until as long as the base voltage of the transistor 2 is positive. The length of the base of the transistor 2 will remain positive, determined by capacitor 3, resistor 3, and resistor 6. Observe the parallel path of the capacitor 3 and its discharge. Alright, view B, figure 3.9 show the waveforms associated with the circuit with the time 1 over the transistor 2 comes out with a cutoff that goes into saturation. Although transistor 1 comes comes out of saturation cut off at the base of the voltage waveform. Transistor 1 shows the positive potential holding transistor 1 cut off at the voltage would normally hold the transistor 1 cut off at the point time interval 2 and 3. And however, the time interval 2 and now the trigger is applied with the base of the trigger transistor 1. Cover them with the conducting of the transistor 1 going into saturation transistor 2 cause to cut off. And the action repeats again each time the trigger of the time 2, time 4, and time 6 is applied. Alright, figure 3.9 shows the trigger to stable the multivibrator output, input voltage is, alright, the PRT, the input trigger that must be short with the normal free running of the phase repetition time of the stable multivibrator trigger phase repetition frequency must be slightly higher than the free running phase repetition frequency. Circle this is to maintain trigger control of the phase repetition time. Alright, your monostable multivibrator. The monostable multivibrator, some call it the one-shot multivibrator, is square or rectangular wave generated with one stable condition with no input signal quiescent condition, one of the amplifier conduction over the other cutoff. Monostable multivibrator is basically used for the pulse stretching as used with the computer logistic systems, communication, and navigation equipment. The operation of the non-stable vibrator relatively simple. The input with the trigger with the pulse voltage with the output chain with the 1 voltage level to the different voltage level. Output remains the 2 voltage level to different time period of time. The circuit automatically reverts its original condition remains in the way until another trigger pulses it to input with the non-stable monostable with the multivibrator action that takes either of the input triggers, converts them to uniform square pulses as shown in figure 310. All square output pulses there is the same amplitude time duration. Figure 310 shows the monostable multivibrator diagram. Multi-stable multivibrator. The schematic of the non-stable multivibrator shown in figure 311. Like on a stable multivibrator, one transistor covers and conducts the other cuts off when the circuit is energized. Figure 311, the monostable vibrator schematic. Or you have your input going in the capacitor 2 with the base, the emitter going grounded with the collector going through the resistor 1, capacitor 2, capacitor 1. The resistor 5, the voltage bias basis, resistor 3, resistor 4, transistor output. Alright, recall with the stable multivibrator with versus energy out of the it was impossible to predict that the transistor would initially cut off the cover over the circuit with a symmetry one shot with a circuit that is not symmetrically like a stable multivibrator. The positive voltage is applied with the resistor 5 at the base of the transistor 1. The positive voltage of the transistor 1 cut off the transistor 2 saturates because of the negative voltage applied with the voltage current collectors to the base of the resistor 2. The resistor, therefore, transistor 1 is cut off. The transistor 2 is saturated before the trigger pulse is applied. It is shown in figure 312, but the circuit is shown in the stable state. Let's take a more detailed look at the circuit condition stable to refer to figure 312 with the edge stated above the transistor 1 cutoff with no current flow with the resistor 1 the current the collector with the transistor 1 with the voltage current collector transistor is saturated practically no voltage drop across the collector essentially 0 volts. Resistor 5 and 3 form a voltage divider on the resistor bias ground potential for the collector transistor 2. The tie point between these two resistors positive. The base over the transistor 1 holds the positive the negative of the transistor 1 and remain cut off. The transistor 2 will remain saturated before the cover the base of the transistor 2 with a very slightly negative against the result of the voltage drop across the resistor 2. If the collector of the transistor 1 is negative voltage current collector of the base of the transistor 2 with near ground, this capacitor must be charged nearly to voltage current collector volts with polarity shown. Now that all the components and voltages have been described in the table set, let's see how the circuit operates in figure 313. Assume the negative voltage applied with the input terminal capacitor 2 coupled with the voltage across the base for the transistor 1 and starts transistor 1 conducting. Transistor 1 quickly saturates and the collector voltage immediately rises to the ground potential for the sharp voltage increase the coupled with the capacitor 1 to the base capacitor transistor 2 the causing transistor 2 to couple the collector voltage of the transistor 2 immediately drops the voltage current collector. The voltage divider of the resistor 5 and 3 holds the base of the transistor 1 negative while the transistor 1 is locked in saturation. Figure 313 shows the monostable multivibrator triggered. One-shot multivibrator has now been turned with applying the pole of the input, but it will turn itself off within a period of time. To see how this is done with the figure 313, again, the transistor 1 is held at saturation and negative voltage applied with the resistor 3 base of the circuit cannot be turned off. And notice that base of the transistor 1 is connected with the capacitor 1 with the positive of the capacitor 1 to keep the transistor 2 cut off. Remember the positive voltage chain with the essentially poles was coupled with the collector with the transistor 1 with the beginning with the connected to the base of the transistor 2, placing transistor 2 cut off. When the collector of the transistor 1 switches the voltage, current collector volts to the 0 volts. The charge over the capacitor 1 acts like a battery. Negative terminal with the collector of the transistor 1. The positive of the terminal connected base of the transistor 2. The voltage will cut off of the transistor 2, but the capacitor 1 will now begin with the discharge of the transistor 1 ground back through the voltage current collector with the resistor 2 other side of the capacitor 1. The time required for the capacitor 1 to discharge depends on the RC time constant of the capacitor 1 and resistor 2. Figure 314 for the timing diagram will show that it's negative of the input pole of the resonant resultant waveforms that would expect for the circuit description. 314 shows the waveform non-stable multivibrator triggered. The only operation not discussed in show for so far is capacitor 1 charge time that occurred right after the transformer transistor 1 and transistor 2 return to the stable state for the assembly time required for the capacitor 1 gaining the electrons left of the side of the charge at the time of the resistor 1 capacitor 1 time constant. Another version of unstable vibrator shown in figure 315 with UA that is on circuit with a UB that should be associated with waveform stable condition in the time interval T0. Transistor 1 is called with the transistor 2 connecting the input trigger with the pole of the positive pole of the transistor time interval 1. Applied with the collector transistor 1 coupled with the capacitor 1 base with the transistor 2 causing the transistor 2 to be coupled with the collector voltage of the transistor 2 goes for the voltage current collector, the more negative voltage of the collector of the transistor 2, the forward bias of the transistor 1 through resistor 4, the forward bias of the transistor 1 conduct with the collector, the voltage of the transistor 1 goes to about 10 to volts. Capacitor 1 now discharge with the keep it up with the transistor 2 cut off with the transistor 2 remain with the cut off with the capacitor 1 discharge with enough to allow transistor 2 to conduct with the time interval 2. When the transistor 2 conducts again, the collector voltage goes again towards 0 with the transistor 1 cut off. The circuit return to the quiescent state with it has been completed. Cycle circuit remains stable until the next trigger arrives in time interval 2-3. Alright, 315 show the monostable multivibrator wave shape schematic. Figure 315 show the monostable multivibrator wave shape forms. Alright, know that resistor 3 variable the slope allow for the adjustment of the gate width, increase the resistor 3, increase the discharge of the time of the capacitor 1, increase the cutoff time of the transistor 2, increase the volt value of the resistor 3 wide at the gates. To decrease the gate width, decrease the value of the resistor 3 with the figure 316 show the relations between the trigger and the output circuit with the view A of the figure show the input trigger the view B and C show different gate width available to the resistor 3 and all the duration gates are different with the duration of the complete cycle remains the same and the pulse repetition of the triggers view D with the figure with the illustrator the trailing edge with the positive alteration variations. 316 show the monostable multivibrator waveforms vibrator gate. Phase readiness time, gate width, monostable. The reason the monostable vibrator is also called the one-shot multivibrator can easily be seen that every trigger applied with the multivibrator complete cycle or a positive and negative alteration output is completed. Your bistable multivibrator. It names and poles of the bistable multivibrator with its two stable state with the trigger with the correct molarity amplitude, but applied with the trigger with the chain with the shape of the remaining with the trigger again. Trigger need for the fixed phase ready repetition frequencies. In fact, the triggers are the different sort of occurring with the different times that can be used with the switch to the circuit. The bistable multivibrator circuit is associated with waveforms shown in figure 317, view A and B of the respectively in the circuit with resistor 1 and resistor 7 of the corrective load, resistor voltage dividers, resistor 1, 2, and 5. Provide force bias of the transistor 2 with the resistor 7, 6, and 3. Provide force bias of the transistor 1. The resistor also couple the collector signal with the one transistor base of the other. Observe the direction coupling with the feedback. The type of the coupling required with the circuit depends on the input trigger with the operation of the on RC time constants inside of the circuit about the transistor with the common emitter resistor 4, which provides the emitter coupling with the capacitor 1 and capacitor 2 with the input trigger of the transistor base. Figure 317 shows the base multivibrator waveforms. And then 317 show the bistable multivibrator waveforms. Note that the circuit is symmetrical with each of the transistor amplifier with the same component with the value of which, when the power is first applied, the voltage divider of the networks become placed with the negative voltage in the bases of the transistor 1 and transistor 2. For the transistor forward by both conduct, there is some slight difference between the circuit. The one transistor will conduct more than the other. Assuming the transistor 1 conducts more than the transistor 2, the increased conduction of the transistor 1 collector of the voltage of the transistor must be less than the more voltage dropped across the resistor 1. The decree for the forward bias of the transistor 2, the decree for the conduction of the transistor 2 for the conductor 2 conducts less, as the collector voltage becomes the more negative, the negative voltage chain of the collector transistor 2 coupled with the base of the transistor 1 causes the transistor 1 to conduct even more heavily. Regenerative action continues until the transistor 2 for the cutoff of the transistor 1 is saturated. The circuit is unstable state, remains until the trigger of the change of the state. Alright, at timing 1 negative, the trigger is allowed with the both base of the capacitor 1, capacitor 2. The trigger does not affect with the transistor 1 with the sense of the already continuing the trigger overcome with the cutoff bias of the transistor 2 with the cutoff of the conduct. Transistor 2 goes within conduction, collector voltage become positive with the positive going change of the transistor 2 with the collector curve with the reverse bias of the base of the transistor 1. If the conjunction of the transistor 1 increase the cutoff point with the collector voltage become negative with the switching action causes the rapid change of the state with the transistor 1. Transistor 2 conducting transistor 1 cut off. A time interval 2, negative trigger is applied with both of the base of time of the transistor 1 brought with the conduction of the regenerative switch or the action of the cutoff of the transistor 2. Bistable Multivibrator will continue the change of the state with the low of long of the triggers are applied with no for the input trigger is required to produce one gate with one turn into and another then turn off the input frequency. Input trigger frequency is still the output frequency. Are your Bistable Multivibrator? Most techniques should know the commonly named other names. The Astable Jordan circuit, more commonly known as flip-flop circuit. The flip-flop is a multi-stable vibrator by meaning 2. That is the flip-flop with the 2 stable state. The flip-flop can rapidly flip from one state to the other, flop back to the original state. The voltmeter where the connected the output flip-flop would be either the small positive negative voltage or a particularly low voltage, essentially 0 volts. No matter what the voltage measured, the flip-flop would be able to remain stable to maintain means of the flip-flop will remain particular state identified, but it will not change the states unless the proper type of trigger pulse is applied. 3/18 of the basic flip-flop. No, it's just symmetrical. Our flip-flops are either the switching circuit applicated for the computer logic operation of the counter shift with the register counter clock pulses generated with the mercury circuit with the RLC with the relay counter control function for very simple application radio communication systems. Note of the basic flip-flop illustrated in figure 318 the 2 input, 2 output. The inputs are coupled to the base for the transistor. The output for the coupled with the collector for the transistor. Think of the flip-flop 2 common emitter amplifier circuits. When the output of one of the amplifier connected to the input of the other amplifier, the vice versa. Point D with it connected through the resistor 4 and capacitor 4 with a point A. Point A is the input to transistor 1 by the same token to point C, which is the output of the transistor 1 connected with the resistor 3, capacitor 3, and the input point B with the transistor 2. Alright, take a close look at a flip-flop circuit. You should be able to see how it maintains stable condition. Typical value of the resistor applied voltage is shown like a 319. The capacitors have been removed simplicity. 319 show the flip-flop capacitor is removed. Alright, 2 voltage divider networks extend with a negative 10 volt with the plus 6 volts. 1 voltage divider with the resistor 1, resistor 4, resistor 6 applies the bias voltage with the base for the transistor 1. Therefore, other voltage of the divided resistor 2, 3, and 5 is supplied with the bias voltage of the transistor 2. Assume the transistor 1, figure 320 with the initial saturated of the transistor 2 with the cutoff, the with the voltage drop of the base for the emitter with the saturated transistor is essentially 0 volts. In fact, with the plate of the base of the transistor 1, good potential of the voltage developed, and voltage divider voltage recurrent current collector resistor 4, 6, 4, 1, and voltage base bias are shown figure 3 in the figure 320. Flip-flop voltage divider. Okay, since no current flow with the transistor 2 with a very little voltage drop across resistor 6, approximately 1/2 a volt of the voltage of the output of the 2 wouldn't be necessary. The negative 5 volts ground, approximately voltage current collected. The voltage of the negative 9.5 consider the high output. Figure 320 is going to show the way of the other voltage divider network. Alright, figure 321 show the flip-flop transistor 2 voltage divider. Transistor 1 saturated with large current flows through resistor 5 of the meter measure approximately 0 volts with ground potential at point C with the man. Notice that the point B is located between point C at 0 volts and a voltage bias volts at 6 positive volts. The meter should be measured with the positive voltage at 0 to 6 positive 6 volts at the base of the transistor 2 point B. A positive voltage of the base over the positive and non-positive, positive, negative, positive. The transistor will cover the transistor cut off the one over the transistor saturated. All of that must be cut off with the flip-flop and stable the transistor. The capacitor will remove at the figure 319 must be returned flip-flop as shown in figure 322. Change the state of the flip-flop from one condition to the other. Capacitor 3 and 4 transmit almost instantaneously. Change the voltage collector with the one transistor the base of the other. Capacitor 1 input chain coupling capacitors. Our figure 322 show the flip-flop. As before, you assume with the transistor 1 saturated with the transistor 2 with the cutoff of the 2 methods available to cover the flip-flop chain with the current state of the first positive going pulse can be applied with the input 1 cover the transistor 1 chain with the saturation cutoff. Second, same result with the achieved with applying with the negative pulse given the input 2 with the transistor 2 would then be chain with the cutoff saturation. Normally, pulse applied with the saturated transistor cover is to be cut off to any input signal but pulse which is correct for the polarity chain with the state of the flip-flop is called the trigger pulse. Figure 323 show the pop of the going trigger the pulse that has been applied with the input 1. The flip-flop is now chained with the state of the transistor 1 cut off transistor 2 saturated. If the second positive going transistor trigger pulsing with applied with the input 1, no effect with the base. Only because of the transistor 1 is already cut off, therefore the pop of the pulse of the back base has no effect with the but is not pop of the going trigger pulse will apply with the input 2. The flip-flop would change back to its original state in figure 324. So far for the basic flip-flop has used only with the positive negative positive transistor. They can also be just easily the negative positive negative transistor. The function operation would not change with only parallelators required with the conduction of the cutoff change. Technician may see that either type of the transistor, positive negative or negative positive negative, symbolic block diagram sometimes even avoid confusion of voltage parallarities. A special kind of block diagram is adapted the same symbol for the flip-flop shown with figure 325, 326. The input for the two inputs that represent with the line with the left and outputs for the lines input for the inputs of the flip-flop are set. Clear outputs of flip-flop are 1 and 0 with the trigger pulse, but they also apply with the set input with the causing input with the positive and negative voltage depending on the type of the transistor. At the same time, the 0 equals 0 volts. This is called the condition set state. Alright, 325 shows the flip-flop, set state, the trigger pulse of the 1 is equal to voltage, 0 voltage, trigger pulse, flip-flop, clear state, trigger pulse, 0 volts. Alright, your trigger pulse applied with the clear input with the positive and negative voltage produces 0 volts with the output with the 1 output goes to 0 volts, so this is called the clear state, that's shown in figure 3, and shown in figure 326. Jumping the state of flip-flop, you can measure the 1 or 0 output measuring 0 volts with the input, 1 input output with the indicator for the flip-flop with the clear state, but the output with is either measured positive and negative voltage, which indicate with the flip-flop is clear state. Either way, the only reading necessary. In figure 327, the flip-flop of the state, set state is prior with the time 0 with the negative voltage with the 1 output. Now this compare the chain with the output voltage with each for the time 0, time 1, time 2, and time 3 with the input pulse starting with the figure. Should help you understand the flip-flop work with the positive pulse at the time 0 with the clear input shift of the FF, clear with the state, stay with the negative voltage of the 0 by output of the time and positive of the pulse. Set increase input drive of the 1 output of the set state with the time 2, the positive pulse, the clear input drives 0 output with the clear state at time 3, and another pulse with applied with the clear input, but the input has no effect with the after this is already clear state. Alright, some flip-flops are third input led with the shown in figure 328. The third input lead is called the toggle to input. Every time with the toggle, so every time the pulse is applied with the T input with the flip-flop chain with the state with the wherever the state is previously the 2000 current rectifier 1 and 2 over the steering network. The steering network is direct for the power of the input with the saturated transistor cutting in the car. Causing you to cut off the negative pulse of the block for the diode, but notice that the negative positive negative transistor where used the diodes would have to be reversed if the toggle signal would have the negative. For example, assuming the transistor 1 saturated transistor 2 cut off the pulse, positive pulse applied with the T input, the input pole for the directed pole for the transistor, the positive pole for the will affect transistor 2 simply with it is already cut off. On the transistor 1, however, the width of the conduction will be cut off, causing the transistor 2 to become saturated. Transistor has reverse state, as in block diagram represents the multivibrator output shown on the toggle input signal and shown by the figure 329. Start with the figure helps you understand flip-flop works each with the toggle input with the case, cover the output with the chain state with the figure 330 show the weight happens when the triggers are applied with the three inputs of the flip shown in figure 328, assuming the flip-flop in figure 330 clear state of one output with 0 volts, 0 volts, output is higher with the timing 0, the timing 0 at the trigger. Apply to set the input flip-flop chain to the next clear input with the trigger with the flip-flop and returns clear. This is say the toggle 1, toggle 2, toggle at time 2, cover the flip-flop the chain state. And once again, the set with another toggle chain with the flip-flop clear state with time 3. Note if the toggle trips flip, multivibrator regardless of the previous state, but then the set with the input with the trigger 4 flips, the flip-flop clear input poles of the trigger 5 clear, cover the clear circuit clear, the clear input with the time 6 has no effect on flip-flop and already within a clear state. Figure 328 shows the flip-flop with the 3 inputs. Block diagram, single flip, flop, the toggle input, 330 flip-flop, the 3 input block diagram. Alright, remember the set input with the set flip-flop with the clear state, but otherwise it will not do anything. Trigger the clear input with the clear, the trigger with the set with the trigger to apply with the toggle input with a bistable multivibrator chain with regardless of the state it's in. Alright, your blocking oscillator. Blocking oscillator. The blocking oscillator is a special type of the wave jam with the U for the narrow pole for the trigger of the blocking oscillator. It has many U for the bunch waves for the concern with the timing. Some of the other circuits they can be with the frequency divided with the counter circuit with the switch, other circuit with the in on off at a specific time. With the blocking oscillator pole for the width over the pulse repetition time and the pulse repetition rate. Are controlled with the side of the different of the certain capacitors, resistors, operating character for the transformer. Transformers primarily determine the duration shape of the output. We cover the important circuit of the transformers action with the RL circuit that we'll discuss briefly. You will may want to review the transformer action in the Neets modules 2, introduction, alternating current transformer before going into the next section. Transformer action, figure 331 view A show the transformer resisting both primary and secondary circuit of the switch 1, flow of the current flow with the resistor 1, inductor 1, the current increase with the inductor 1 increase with the induced the voltage with the inductor 2, the coil of the current flow of the resistor 2, the voltage induced in inductor 2 that depends on the ratio of turns of the inductor 1 and inductor 2 as well as the current flow through inductor 1. Figure 331 shows the RL circuit. The secondary load independent of the resistor 2 effect of the primary independent of the reflector and the secondary prime of the load. The secondary increase of the resistor 2 decrease the load of the primary, increase the primary and secondary current increase. Transformer 1 can be shown with as an inductor resistor 1 and 2 with the bottom of the equivalent series of the resistance of the series of the transformer 1 effect of the inductor of the chain of the resistor 1, resistor 2, the chain of the current of the equivalent circuit the shown figure 331 view B active of the resistor RL circuit that we'll discuss in these terms. The RL circuit. Or your simple series RL circuit. The series on this S1 clove of the series of the RL circuit view B331 active upon the first input source voltage that appears across the current voltage begin with the flow of the over the inductor voltage of the resistor and amperes increase at all exponential rise. Figure 332 view that show the exponential curve in terms of 5 times the constant resistor voltage current. Maximum of the voltage in the inductor is 0. The relationship is shown in the following formula. Our amplitude current voltage. The switch 1 is closed shown figure 331 view B with the current collected flow curve. This is 1 shown for figure 322 view A, 332 view A by the time of curve of the current that reach the maximum percent of the side of the inductor and the resistor voltage. If the resistor voltage is small with the RL circuit, it has a long time current. But if the one small portion of the curve of the C to D, C or to D over the view A with the current increase the maximum chain with the given time period for the small increase time intermits more. Linear current ride with a constant current increase through the coil with the key factor of the blocking oscillator. Alright, we're going to cut the tape there because it started raining.